Law of sines. We previously learned that if you have a right triangle, then sine of an angle is the opposite leg over the hypotenuse. Cosine of an angle, of an acute angle, is the adjacent leg over the hypotenuse, and tangent of an acute angle is the opposite leg over the adjacent leg. Well, those facts and the reciprocals, those are only true if you have a right triangle and if your angle is an acute angle. Well, the law of sines works in a much broader sense. In essence, it can be any type of triangle. It can be an obtuse, it could be an acute, it could be a right triangle. So let triangle ABC be any triangle, with A, B, and C representing the measures of the sides opposite angles A, B, and C respectively. Respectively means in the same order. So little a comes first, big A comes first. So that means that little a is opposite of big A. If I draw that triangle ABC, capital letters are for angles, then the side opposite the angle is the same letter, A, B, and C. So in any triangle in this situation, then the following is true. Sine of angle A over side A is equal to sine of angle B over side B, which in turn is equal to sine of angle C over side C. Which basically means if you take any sine of any angle over its opposite side, it'll be equal to sine of a different angle over its opposite side. When you do this in practice, you're not going to use all three of those. You're going to use two of those at a time. Maybe A and B, or B and C, or A and C. You won't use all three. The next question might be, when would I ever use law of sines? We'd use law of sines in these two cases. Case 1, you're given angle side. In case 2, you're given angle side. Now this case 2 is a really special case. So special that although you use law of sines in angle side, you don't really use law of sines in angle side. That's what we like to call a contradiction. We will discuss this more at a later date. Today we are just focusing on case 1. You're given two angles and the side opposite of one of those angles. The picture would look something like this. Maybe you're given angle A, you're given angle B, and you're either given the side opposite of A, which would be down here, or you're given the length of the side opposite of B over here. Let's say it's like this. In either of these cases, the one we're actually doing or the one we're doing in the future, what's important is that you have a side and the angle opposite that side. If you have that situation, then technically speaking, you can use law of sines to do the problem. This ambiguous case for the law of sines, once again, this applies if you have an angle side, which we said we're going to look at this at a later point. We'll come back to this after we learn a law of cosines. Example A. Determine the number of possible solutions. Well, before we do any more to this problem, if you're given angle side, then there is one solution. If a solution exists, solve the triangle. That means find all the missing measurements. Round angle measures to the nearest minute and side measures to the nearest tenth. Let's first draw this picture. Triangle ABC. Label the angles any way you choose, but the sides opposite those angles should be the same letter but lowercase. Angle A is 25 degrees, 26 minutes. Side A is 13.7. Angle B is 78 degrees. So we are given in this situation angle, side. We know we can use law of sines because we're given angle, side, and an easier way to remember it, in my opinion, we're given a side and the angle opposite that side. Anytime you're given angle side, the number of possible solutions is 1. So this has a 1 solution. So next we are going to figure out one of three things. we could find angle C, side C, or side B. At this point, we couldn't find side C because we don't know the angle opposite of it. We could find angle C right now because if you add up all three angles in a triangle, those are supposed to sum 180. We could also find side B right now because we could use law of sines. We could say sine of 25 degrees 26 minutes over 13.7 equals sine of 78 over C. Let's find angle C first because that is probably the easiest thing that you are used to of doing in the past. According to the angle sum theorem, measure of angle A plus the measure of angle B plus the measure of angle C equals 180 degrees. The sum of the angles in any triangle is 180 degrees. Measure of angle A is 25 degrees 26 minutes. Measure of angle B is 78 degrees. The measure of angle C we don't know. If you combine like terms, 25 degrees 26 minutes and 78 degrees, you get 103 degrees 26 minutes. To get measure of angle C by itself, we have to get rid of this positive 103 degrees 26 minutes. We're going to subtract it from both sides of the equation. If you subtract it from the left, measure of angle C is by itself. If you subtract it from 180 degrees, you're going to get 76 degrees 34 minutes. So we know that the measure of angle C is 76 degrees 34 minutes. That way the picture shows that you have 76 degrees 34 minutes. Continuing, let's find side C now. Using the law of sines, if we take sine of angle A, which is 25 degrees 26 minutes, we write it over its opposite side, A, which is 13.7. According to the law of sines, that's going to be equal to sine of another angle over its opposite side. Well, angle C is 76 degrees 34 minutes. Its opposite side is C. Trying to solve this equation, trying to get C by itself. Since C is on the bottom of a fraction, we don't want it there. I'm going to multiply both sides by C. If I do that, I'm going to get C times sine of 25 degrees 26 minutes divided by 13.7 on the left. On the right, I'm going to get sine of 76 degrees 34 minutes. So I need to get rid of this times sine of 25 degrees 26 minutes over 13.7. The opposite of multiplying by a fraction is multiplying by its reciprocal. So if I multiply both sides by 13.7 over sine of 25 degrees 26 minutes, on the left, those things cancel. On the right, I'm going to get 13.7 times sine of 76 degrees 34 minutes over sine of 25 degrees 26 minutes. If you put this into your calculator, you're going to get C is approximately, the direction said round to the nearest tenth. It's not 31 exactly, it's 31.0. Put the 0.0, which denotes that we likely rounded it. Make sure when you use your calculator, you use it properly. It's likely that it will start a parenthesis every time you have an angle. It's important that you close that parenthesis before you get down here to the bottom. So make sure you type it in, make sure you get that same number, 31.0. Work for side B, we can use law of sines again. Law of sines says if you take sine of an angle, such as angle A, 25 degrees 26 minutes, over its opposite side, A, 13.7, that will equal sine of a different angle over its opposite side. So angle B is 78 degrees, its opposite side is little b. Trying to solve the equation for little b, I'm going to multiply both sides by little b. It's going to give me b times sine of 25 degrees 26 minutes divided by 13.7 on the left. On the right, it's going to give me sine of 78 degrees. Trying to get this b by itself, it's being multiplied by this fraction. The opposite of multiplying by a fraction would be to multiply by its reciprocal. If we did that, we would get b equals 13.7 sine of 78 degrees divided by sine of 25 degrees, 26 minutes. Put this in my calculator, making sure that I am careful to close my parentheses around my angles. I'm going to get b is approximately 31.2. We found all the missing measurements, therefore we solved this triangle and it is completed. Please note, we did not use any rounded numbers to find other answers. It is true that some of our answers are rounded, but we did not use the rounded numbers to find other answers. Example B, use the law of signs to show that each statement is true. These problems, in my opinion, are fun. At first, they are going to perhaps seem to be not very much fun. As you start figuring them out, you will find yourself laughing like a school child because they're just delightful. So, problems like this, you have to start out with a fact that everyone assumes is true, and you have to add facts to that fact that everyone assumes is true, until you eventually get to a point where you've proven what you're trying to prove. So the end result, the last step in what we're trying to do, is going to be what this says here. A plus C over C equals sine of A plus sine of C over C. What's a fact we can all agree on? Well, let's agree on what the law of signs says. Sine of A over A equals sine of C over C. Why did I choose this fact? Simple. I'm going to write down my reason here. This is the law of signs. Reason I chose this fact, if I look at what I'm trying to prove, I need big A's, big C's, little a's, and little c's in the problem. By writing this statement, I've accomplished that. Now I look at where I am, and I look at what I'm trying to accomplish. I notice that all my signs are on the same side of the equation. All my little letters are on the other side of the equation. Also, I notice that C is on the bottom, and the end result, C, is on the bottom. So that C right there is in a pretty good place. I want to leave it there. I'm going to get this A to go over to the other side of the equation by multiplying both sides by A. So I'm going to multiply both sides by A. That's the multiplication property of equality. On the left, if I multiply by A and I'm dividing by A, the A's cancel. On the right, I'm going to get A times sine of angle C over C. So I got my A's and C's on the same side, just like I'm supposed to, which is awesome. Now I want to get my sine of C to go over on the left side of the equation. Right now we are multiplying by sine of C. The opposite of multiplying is dividing. So I'm going to divide both sides by sine of C. On the left, that's going to give me sine of A divided by sine of C. On the right, my sine of C's cancel, and I get A over C. We're in great shape at this point. We're in great shape. We got our signs on the one side and our little letters on the other. This next step might give you a heart attack. Here's what I know. In order to keep my denominators the same, which are C's and sine of C, which is what my denominators are right at this point, but my numerators have to change, I'm going to have to add or subtract something to this fraction. If you add two fractions together, the bottom stays the same. The tops are going to change. So here's what I'm going to do. I'm going to add a 1 to both sides of the equation. At first, this is probably going to seem like I am a psycho for adding 1 to both sides, but watch what happens when I do. So I added 1 to both sides of the equation. If I then get common denominators, like if I change this 1 to a fraction, sine of C over sine of C, so I can add these together, and I change this 1 to a fraction, common denominators, I get C over C. This is what I would get. So once again, I changed the 1 to sine of c over sine of c. Anything divided by itself is 1. I changed this 1 over here to c over c. Anything divided by itself is 1. On the left, it gives me common denominators. On the right, I get common denominators. So this is substitution property of equality for real numbers. I replaced the 1 with something that was equal to it. Once you have common denominators, you are to add the numerators. These numerators are not like terms, therefore I cannot actually write them as one term. That once again is the substitution property. I substituted 2 fractions with 1 fraction because they're equivalent. Now if I look at what we're trying to prove, we're super close. Sine of A plus sine of C over sine of C equals A plus C over C. What's wrong about it is this is supposed to be on the left side and this is supposed to be on the right side. Can we switch it? Only if we have a reason to switch it. This is supposed to be a little c here. Somehow it got big. What property says that you can take an equation and put what's on the left on the right and the right on the left? That's the symmetric property of equality for real numbers. The end result is we have what we were trying to prove. We made a logical step every step of the way. So we're finished with this problem. A couple of notes. Note 1, there is no right way to do these problems. In other words, there's not one right way, I should say. There are an infinite number of ways to do the problem that I just did that are equally good as what I just did. You could take more steps than what I did, depending on how you did it. You could take less steps if you did it in a more efficient manner. The order in which some of these steps were in could have been done differently. The important thing to do, as always, if you don't know what to do something. And it's likely that something will lead you to something else. Well, enjoy your day. Please do your homework over law of sines. Thank you.